thank you so much for inviting me for the talk. And so we're going to share with you some really exciting findings that we have found on a sample returned by the first Hayabusa mission. Right, so let me go back to the title slide. So we're going to talk about this mission, the first Hayabusa mission, which came back to us a decade ago. So recently, the second Hayabusa mission just came back in December 2020. So we're talking about this first mission, results coming from the first mission. So you can see how we continue to milk data coming from mission that was coming back a decade ago. So we continue to look at sample returned by space mission, and we're continuously milking information from Hayabusa or Apollo in the 60s or Stardust in 2006, etc. So the next slide, you'll be able to see those missions that I mentioned to you just previously. So these are all different sample return mission, and the yellow symbols are highlighted here, those that are with mandatory of returning samples for analyzing organic material. And others are, but also the yellow symbols missions are also those that visited small solar system objects, and others in gray, you could see there are missions that went to the moon, the Apollo mission, the lunar mission, Chang'e's mission, and Martian moon MMX, and also to collect solar wind particles. So these are all missions that returned material from a different planetary body in our solar system. But we have so many meteorites on Earth. Why do we still need to bring back sample from extraterrestrial contacts for us to study in laboratory here on Earth? It's because of two main considerations. So first is that there is very compared to meteorite fell on Earth and collected on Earth, the sample return mission return samples with least contamination. It still contains some contamination occurred during different processes, but it is one of the least contaminated material, and these samples can be then analyzed by state-of-the-art instrument here on Earth compared to in situ analysis by other space missions. So sample return missions are very exciting. So thank you, Ashley, to talk about the exciting Winchcombe meteorite and link to what we are capable of doing in laboratories here on Earth. But meteorites are an example of things that are coming from asteroids and other solar system body as well, but quite a lot of them are coming up from asteroids. So asteroids are primitive geologic remnant of our early solar system. They have not been melted in the past, so they retain information about the birth of our solar system. So they contain a lot of information that we were able to milk and collect about the early stage of our solar system formation. Another reason why we need to, or we want to go to an asteroid to study them, is not because asteroid orbits in different places, but some of them orbit quite closely to the Earth, and some of them even cross path of the Earth. And we wanted to understand why, and then we would like to know what would happen to if they really cross path the Earth. And finally, the significance to the origin of life. How water and precursor molecules got delivered from these extraterrestrial bodies to here to Earth before the onset of life on Earth. So there are a few different locations where you could find asteroids. There are for example, the main asteroid belt, which is located about 2.2 to 3.2 astronomical unit. Astronomical unit 1 of it is the distance between Earth and the Sun. So asteroid belt is about 2 times of that at least. And there are 2 other places where you could find also asteroids. Some are called Trojans, where they orbit pretty close to the orbit of Jupiter, and the other ones are called near-Earth asteroid. As you can see, there are pretty close to the Earth. The orbits are pretty close to the Earth. And what's another thing that you will notice is on the right figure here, you will see a asteroid distribution throughout our solar system. So the one here highlighted in yellow is where the main asteroid belt is. So you can see most of the asteroids are found in that region in the main asteroidal belt. And you would expect to see that when you talk about asteroidal belt, you would think that maybe it's going to form like a kind of like a bell-shaped distribution where you've got the most number of asteroids in the middle of the asteroid belt, and then it is fan outward, something like that. But it is not. So you can see there are like mountains feature with gaps between different bands at different distance from the sun. So that tells us that somewhere in our solar system, the asteroid is not stable. Their orbit cannot maintain stability within those gaps. Those are called Kurtwood gaps. So another thing that's interesting is what I'm showing you here is a figure of different asteroids again, but the vertical axis is now this new image that pop up is optical inclination. So it tells us that there are different families of different asteroids. So you see some clustered area here, some clusters here. These are asteroid families. They are what we thought to be fragments of past asteroidal collision. So there are two things that we wanted to point out. One is that asteroid coming from the main asteroid belt, but when they fall close to the Kurtwood Gap, they would no longer be stable and they will be expelled from the region outside of the outer solar system or into the inner solar system. They would go out elsewhere. And second is some collision happened in the past that formed this cluster of asteroids. Right. So the question is how they travel from the main asteroid belt to the near Earth orbit. What's the material mixing would be like? As you can see down here, there are different types of asteroid of different, if I could show you my mouse here, pointer option, laser pointer. So down here, I don't know which I could see two pointers on my screen. I'm hoping you can see the right one. So on here you can see some C-type asteroid, S-type asteroid. So there are different asteroids of different spectral characteristics, and they distribute different places and they in throughout our solar system. So how this material got mixed and how volatiles coming from maybe outer solar system travel all the way to inner solar system and arrive at where the Earth is. So here, this is the cluster or the orbit of different type of near-Earth asteroids. So these are really close to the Earth. And you can see that the most abundant type of near-Earth asteroid, NEA, are the Apollo asteroids. So they're in orange color. So you can see that they cross path of the Earth's orbit. So that means that they will have the potential of colliding with the Earth. Quite interesting to know. And Itokawa, the target of the first Hayabusa mission, as well as Ryugu, the target asteroid of the second Hayabusa mission. They are both the Apollo type asteroids, so they're the most common type of near-Earth asteroid, and they orbit quite close to the Earth, and this is the mission that went around so first they swung by the Earth and go along the orbit of Itokawa, observed Itokawa, and went down on Itokawa, collected sample and brought back to Earth. So it was basically the history of Hayabusa mission. And during the observation, we have found something quite interesting. It's that so asteroid Itokawa is S-type asteroid. So when I talk about the spectroscopic characteristic, it belongs to the S-type asteroid. It's different from the C-type asteroid. C-type meaning is more enriched in maybe carbonaceous material, usually darker type of asteroids. But S-type asteroid, which Itokawa is S-type asteroid, is silicious, is brighter. But interestingly, on top of it, you can see a dark black boulder. It's called a black boulder, and it's nothing similar to the rest of the asteroid. It's very black. It looks more like carbonaceous material, carbonaceous asteroidal material that got landed on S-type asteroid. So it's very interesting how this could happen and what kind of dark material this C-type or darker type material could bring to Itokawa and change its content. So that's very interesting that we wanted to know. So the way to really find out is then we performed touchdowns and collect samples from the surface of it. So Hayabusa was originally planned to fire projectiles onto the surface of Itokawa asteroid and kick off dust to collect samples through the sample horn, into the sample chamber here. Sample chamber room A, room B. But for some reason, those projectiles were not fired due to, for example, safety concerns during the touchdown operation. So both touchdown did not fire the projectile, so the only sample that could collect it into the sample chamber, which is some dust that probably kicked off during the touchdown motion. So only very tiny amount of samples were returned by the first Hayabusa mission. So before we open the sample, there are some CT scan that look inside of the sample chamber to see what's inside. As you can see, not much. It's pretty much empty. And when they look at it from the top of it, where they install a like a window that you can look inside of it, again you don't really see much really. Yeah, let me increase that size for you to really see much detail. You can't really see much because there was really not much. And that sample of grain is here. I hope you could really still see my pointers down here, one of the grains. So what happened was people were scared. I think I would be shocked when I was in the, well, kind of shocked and not shocked, but like what we're gonna do with this looks like empty space. So what people did was the scientists did was to flip the sample container upside down, and what they did was they did use a very clean screwdriver to hit to tap the sample chamber for 20 times. It's published, and they dislodged a number of tiny particles onto the glass slide. One of them is pointed here in the yellow arrow here, is the largest particle is about 300 micron in diameter, in size, 300 micron, the largest particle. So it was challenging to analyze the sample. The way to do that is for a sample to pick the sample up with the needle using static electric. So instead of using a forceps or your hand, you cannot use your hand, but instead of using all these tools, you need to use a needle for a sample to pick the sample up. So it's really a really scary and very challenging analysis. And what we did was we've got one sample that got allocated. It's half the size of a human diameter of a human head, that sort of size. We look for organic matter and water in that sample. So when we talk about organic matter, basically anything that contain these life essential elements. And they usually contain two forms of organic material in extraterrestrial samples, including soluble organics like amino acids and insoluble organics like macromolecular carbon. So in this talk, I'm talking about the macromolecular carbon down there in the purple box. So here it is. We call this sample Amazon. So it's this the sample number. We call this sample Amazon because it resembles kind of South America. We did debate whether or not we should call it South America or Africa, kind of similar, but we decided on the South America anyway. Pretty small particle, but we were able to do a lot with it. For example, we started with Raman spectroscopy. It's capable of telling us the mineralogy as well as the organic maturity. So these are from previous analysis of other samples. But what it shows here is from using Raman analysis, you'll be able to tell what mineralogy, so what mineral it's composed of, and even some glimpse of the chemistry of the mineralogy. And organic maturity. So these are the G bands. I will show you later what G bands are, but the G band components and the variation in the heating, the peak heating temperature will give you different signature. So that basically tells us a lot about that Itokawa particle, Amazon. So from that, here is the particle that a different color represents a different thing based on Raman analysis. So the green one are the olivines, and the blue colored here are albites, and yellow are organic material, and red ones are pyroxenes. And we can see mostly pyroxenes are associated with organic material, and the mineral composition and the chemistry of it is pretty close to other Itokawa particles. So we know that, okay, this is a Itokawa sample. It's not coming from a hair or something. Then we look at the organic content. We saw organic material that has been heated to about or at least 600 degrees Celsius. Oh, sorry, the peak metamorphic temperature is 600 degrees Celsius, next to something that's not been heated over 200 degrees Celsius. And when we look at the less heated organic material, we also use nanosims to look at the isotopic composition. And what it tells us that is that the deuterium, the carbon-13, nitrogen-15, they are showing an ambiguously extraterrestrial or isotopic signature. So terrestrial organic matter down here, and Itokawa is all the way up here. So very significant result showing is indigenous organic matter belong to extraterrestrial material. But that's one thing that's very interesting is why it has been heated so that much. Some of the material not heated, some of the material got heated so bad. So heating on asteroid can be done, for example, by internal heating. That will give you an onion shell kind of heating grade. So 6 represent more heating and less heating when you go to outer shell. But what we saw for some rubble pile asteroid and for what we saw for this Amazon particle is some heated material right next to unheated material. So there has to be some sort of collision happened that fragment and caused Itokawa to form into a rubble pile. And on the right hand side here is a figure that estimated the size of the original Itokawa asteroid based on the temperature, based on the CII formation time, for example. And what that tells us that is Itokawa should be something that has a radius of larger than 20 kilometers in size. 20 kilometers in size in radius, 40 kilometer diameter. And remember, Itokawa is a asteroid that is less than a half a kilometer in diameter. It's much smaller. So what it's supposed to be, the size of its original size, is at least 80 times larger than what it's looking like. So it has to be that it was catastrophically impacted in the past and reformed, reaccreted into the current smaller size Itokawa. So during that catastrophic impact, what will happen to the asteroid's water? So we look at the water and we find that the water is pretty depleted in olivine. So it's not much water in the olivine. But then when we look at the albite, late forming albite, is more enriched in water. And by the schematics of deuterium ratio and the water abundance of the nominally anhydrous mineral like olivine, for example, it tells us that there has to be a mixing between water of carbonaceous asteroid to Itokawa. So asteroid Itokawa has been evolved by gaining foreign matter, just like the ancient Earth. So what we're doing next is we're going to do more analysis for the amino acids, and this will not be shown in this talk. We'll be talking about that in the future. So quick summary. Amazon gained, so asteroid Itokawa was so big, it's heated so badly, and water lost, organic heated in the past. and it even got shattered by another asteroid, got catastrophically impacted, and then it reformed into its current size. It's no longer heated at that size, but it continued to evolve by gaining extraterrestrial water, extra asteroidal water throughout its history. So I'm going to stop here. I think time is about up, and we'll see if there's any question that maybe I could answer one before we end for the AGM.
Okay, thank you, Queenie. That was really fascinating talk. Yes, absolutely fascinating. I think there'll be definitely lots and lots of questions. There's a question. I think we'll take one question and then we'll go into the AGM. Please try and stick around for the AGM. It's really important, I think, for people to be here for it. But I'll just read out one from Jane Barling in the chat, which says, are all the Apollo-type asteroids chemically the same? Could they all be from the precursor body for the particle you worked on?
The Apollo type asteroids are not all chemically the same. For example, the Ryugu and asteroid Itokawa, they are both the first and second, vice versa, of the Hayabusa mission. One of them is carbon rich and one of them is carbon poor. So like the one that I analyzed is supposed to be carbon poor. So they spectroscopically and chemically, mineralogically, they would look different. It's just that they happen to travel to close to the Earth and orbit around the Earth in a similar way. I hope that answers your question.
I'm sure it does.